So we're at the final subchapter of chapter 3, the normal distribution for year 13. So it comes to the crunch here. So today we're going to be looking at how the normal distribution can also be used to model the sample mean as well as the distribution itself. So for example, if a random variable is normally distributed, the distribution of sample means taken from that population will also be normally distributed. So that's going to be the focus of today, underpinned by a fair few worked examples together. So you can probably guess what I'm going to say now. There are a couple of warm-up questions for you to have a go at. Here they are. Normally give more than 2, but I've made question 2 quite big, just off the back of the last subchapter, which was fairly hard going. So question 2 is just to give you even more of a bedding in of the skills we talked about last time. Question 1 is more year 12. Question 2 is full-blooded year 13. So press pause now and try both of these as best as you can. Press play to just see if your solutions match mine, and if not, hopefully this recording will help you to understand where you may have gone wrong. So without going on any more, let's talk through question number 1 of this warm-up. So we have an 8-sided dice labelled 1 to 8 used in a board game. It's suspected of not giving a score of 1 often enough, so it's biased against a 1, is the suspicion. So during a particular game, it was rolled 40 times, and the number 1 only appeared twice. So test at a 5% significance level whether the probability of a die landing on 1 is less than 0.125. State your hypotheses clearly. So what we can say here is if we let the distribution of dice rolls be big X, and this is the distribution of how many times 1 appears, then it's either going to be a number 1 or not. So it will be binomial. So it's 40 throws in total, so it's going to be 40, and the probability of landing on a 1 is 0.125. So assume this to be the case via H0. So H0, the null hypothesis, we're going to assume that the probability of landing on a 1 is 0.125. The alternate hypothesis, the suspicion here is that it doesn't land on a 1 often enough. So it might be that the proportion of the times it lands on a 1 is actually less than 0.125. And I'm just saying here that P is the probability of landing on a 1. So we imagine it on a distribution. So I always tend to draw these out. So the distribution will be peaking at the expected mean and going less and less common at either tail. So if it was a 0.125 chance, which is a 1/8, we'd expect about 1/8 of these 40 rolls to end with a 1 showing. 1/8 of 40, we'd expect typically 5 1s to appear. So here, we've got that only it's appeared twice. So what was the chance of that happening or less? So we need to work out this proportion here and compare it against the critical value. So by H0, the probability of having seen 2 or fewer 1s is this proportion here we're trying to work out. We're going to compare this against the 5%. So on the calculator, we're going to go menu, option 7. I'm going to go for binomial CD. So scroll down and press option 1 and press 2 for variable. So this time, we want to work out the probability of up to 2 out of 40 1s appearing, where the probability of 1 appearing is 0.125. So press equals and press equals again. We get here about 0.1084. That's about an 11% chance. So that's greater than the significance level we're testing against. So that's greater than 5%, which is 0.05. So in other words, the significance level here is smaller than what we've observed. So although getting a 2, 1 or 0 is fairly rare, 11% isn't as freakishly rare as 5%, so therefore we'd actually accept H0. This isn't critical, so therefore accept H0, assume the probability of a 1, probability of a 1 is equal to 0.125. So this bit here is about 11% of the curve. For it to have been critical, for 5%, we would have needed something in this region here, where that's 0.05. So 10% isn't quite in the extreme enough tail for us to reject H0, which is why we accept. Number 2. A company has a customer service call centre. The company believes that the time taken to complete a call to the call centre may be modelled by a normal distribution with mean 16 and standard deviation sigma. Given that 10% of the calls taken, 10% of the calls take longer than 22 minutes, we need to show that to 3 significant figures, the value of sigma, the value of the standard deviation, is 4.68. So first of all, let's just draw this out. So the assumption is the mean is 16 minutes. And if that's the case, it's normal, then this here would be 16. And 10% take longer than 22. So if I draw in at 22 like so, then this bit of the curve needs to be 10%, that proportion. Now here, of course, we don't know the standard deviation. So what we need to do is to standardize into the standard normal curve. So we take this normal distribution and we're going to standardize it now by subtracting the mean from all points and dividing through by the standard deviation. So if I just take the exact same curve, and we can just adapt the values as such, then 16, the mean for any standard normal distribution is always 0, so this is going to become 0. And at this end here, it was 22. We're now going to do 22 minus the mean and divide through by the standard deviation, which we don't know. We're just going to still call it sigma. And this proportion of the curve needs to be 0.10, like we mentioned before. And this is now the standard normal distribution. This is big Z with a mean of 0, standard deviation of 1. So we need to work out what Z value would have given us a probability of 0.9. In other words, if this is 0.10, all the rest of the curve down here will be 0.9. So that's our first step. And because that's 0.90, then we're going to use the inverse normal function. So we need the Z value for what would give a probability of 0.90. So we go to menu, press option 7. This time we go to inverse normal, option 3. We want to work out the proportion of a curve where it's 0.90. What value would give that? The standard deviation for the standard normal curve is 1 and the mean is 0, so leave these as they are. That gives us a value of 1.28155. And so what that tells us is that 22 minus 16 over sigma needs to be equal to 1.28155, and so on. We can now rearrange and solve. So 22 minus 16 is obviously 6. multiply both sides by sigma, so 6 equals 1.28155 sigma. Therefore, sigma will be 6 divided by this 1.28155 and so on. So let's work this out here. So menu 1 to normal mode. The answer's stored, so 6 divided by that value gives us 4.68, which is what we wanted to show all along. So we've proven what we needed to for part A. So for part B, now we know the standard deviation, we can now calculate the percentage of calls that take less than 13 minutes. So we know sigma now, so we can either use a standard curve or we can go back to the original without it being standardized. I'm going to show you how to do it without it being standardized. So this here is the standard deviation. So if I go menu 7 and go to the normal CD, and the percentage of calls which are less than 13 minutes, the upper bound is 13, the lower bound is anything less than 13. So I'm going to make the lower massively small. I'm going to go for minus 999,999. Now this time I know what the standard deviation is now. It was 4.68ish. So I just type in the answer from before, which has been stored, and the mean, we were told, of course, is 16. So press equals and equals again. That gives a figure of 0.2608, which as a percentage is approximately 26.08%. We're next told about the supervisor in the call centre. He claims, or she claims, that the mean call time is less than 16 minutes. Oh, it's a he, sorry. He collects data on his own call times to just double check. So 20% of the supervisor's calls take more than 17 minutes, and 10% take less than 8 minutes to complete. Assuming that the time the supervisor takes to complete a call may be modelled by a normal distribution, we need to estimate the mean and standard deviation of the time taken by the supervisor to complete a call. So this is actually a very dressed up simultaneous equation question. So there's two different things we need to consider. Okay, so we've got two different bits, two different values to think about. So from here, the expected or assumed mean is of course 16. So here's his mean, because we're working out the mean of the supervisor, not of anything else. We're told that 20% of his calls take more than 17 minutes. So if that's mu, this is 17, then up at this end here is 20% of the curve. So that proportion's 20%, 0.20. We're also told that 10% of his calls take less than 8 minutes to complete. So for this one, if that's mu, then 8's down here, and this tiny region over there is going to be 0.10 of the curve. Now we don't know mu, and we don't know the standard deviation. So what we need to do is we need to standardize this to work out what mu is and also the standard deviation. So we just take both and standardize. Then we can work out what mu is and the standard deviation. So these two curves will look the same, they'll have the same characteristic normal shape, only we'll now have to alter the values, because to standardize the normal, what we need to do is we subtract the mean and divide by the standard deviation. And so the mean for all standard normal curves is going to be 0, and so this value here becomes 0 instead of mu. And the other values, we subtract mu and divide by sigma. So this here becomes 8 minus mu, divide by sigma. So if this is 0.20% of a curve, this over here is going to be 0.80. So we need to find the z value that would give us 0.80%, sorry, 0.80 of a curve, 80% of a curve. So here what we're going to do for this one is do the inverse normal, and also we're going to do that for this bit here. So inverse normal twice. So menu, option 7, inverse normal. So for this one, we want this area of 0.80. These are both standardized now. So the standard deviation is 1 and mu is 0. So we need 17 minus mu over sigma to be 0.841620.847. So 17 minus mu over sigma equals 0.841 620.847. I'm not rounding off yet. I need to rearrange this now, so I can multiply all sides by sigma. So 17 minus mu equals 0.84162.0847 sigma. So therefore mu equals 17 minus 0.84162.0847 sigma. We now do the same for this one. So what's the z value to give a probability of 0.10? So we do 8 minus mu over sigma. So here we want the area to be 0.10. So 0.10 gives us a z value required of minus 1.28155. Again, multiply through by sigma, gives us the 8 minus mu equals minus 1.281551638. Therefore mu must be, sorry, that's sigma now. So therefore mu equals 8 plus 1.281551638 sigma. So both are in terms of mu. So what we can do here, we can set this one here, equal to this one. I apologise for that colour, by the way. That colour doesn't make the red very easy to see. I'm going to now change this colour into a different one, if I can. There, that's a bit better. So I can now set these equal to each other. So if I now set 8 plus 1.28, etc. equal to 17 minus this, scroll down slightly, so therefore 17 minus 0.8416 and so on sigma, that equals 8 plus 1.28155 sigma. So if we rearrange, if I add this to both sides of the equation, so I'm going to take the 1.281551638 and add on to this for 0.8416 2.1620847, and I get 2.123 and so on. So then I can say that 2.123, etc. Then if I subtract 8 from both sides, 17 minus 8 is 9. Therefore, I get that sigma, if I do 9 divided by the 2.123 number, 9 divided by that answer here, gives me a value of approximately 4.24 to 3 significant figures. So I plug this in as my answer. I can now sub this into one of the original equations for mu. So therefore I can say, therefore mu, picking this one here, will be 8 plus 1.28 times by this 4.24. That's a decimal, making a picture of this. So mu is going to be this 1.28 figure here times by 4.24. So this figure times it by the 1.28, 1551638, then pop on an extra 8, gives me 13.4. And that, of course, is going to be in terms of minutes. So the mean for this supervisor is about 13.4 minutes. Finally, now we conclude. So state, giving a reason, whether or not the calculations in Part C support the supervisor's claim. The supervisor is claiming that the mean call time is less than 16 minutes. He's tried his. His mean time is about 2.5 minutes less. So it does seem that he's right. If he is no quicker than average, if he's an average person, maybe he's right. So we need to conclude with something like this. So because the mean of the supervisor is less than the assumed mean, in other words 13.4 minutes is less than 16 minutes, these calculations would tend to support the supervisor's claim. Let's get on to the main body of today's session, which is hypothesis testing using the normal distribution. So let's get started. So how do we do this? Well, if a variable, big X, is normally distributed, then the distribution of its sample mean, big X bar, will also be normally distributed. However, because the mean is calculated by taking into consideration many values, the standard deviation of the sample mean will be smaller than the standard deviation of all the values. So for example, if you just sampled one value, it could be here, there, or anything, but if you take many values, then it will average out much better. So in fact, the standard deviation of a sample mean, it's inversely proportional to the square root of the sample size. So the bigger the sample sizes are, the more similar and less varied the means from those samples should be. So this is the important take-home point. For a random sample of size n, taken from a random variable, big X, which is normally distributed with population mean mu and population variance, sigma squared, for the sample mean, big X bar, will also be normally distributed, and the sample mean we model as having the same mean as the entire population, but we divide the variance of the population by n to work out the variance of the sample mean. So what we can do is we can use the distribution of the sample mean to determine whether or not the mean from one particular sample, x bar, so x bar is the mean of the sample, whereas mu is the mean of the entire population. So we can test if the mean from a sample is statistically significant for a hypothesis test. We can test the sample mean, then determine, for example, if we accept H0 for a particular test or reject H0 for a particular hypothesis test. So let's have a look at some examples about how this works. So we're at example 1. We have a company selling fruit juice in cartons. The amount of juice in a carton has a normal distribution with a standard deviation of 3 milliliters. So first of all, we can just write this down. So it's normally distributed. So I'm going to say, let's call it big X. It's going to be normally distributed with a mean, it doesn't say the mean actually, it's a normal distribution. It says standard deviation is 3 milliliters, so the variance is 3 squared. And it says here what the mean is. It's believed to be 60, according to this company. So like I'm saying, company claims that the mean amount of juice per carton is 60, but a trading inspector has received complaints that the company is overstating the mean amount of juice per carton, and he wishes to investigate this complaint. The trading inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1 milliliters. Shock, horror, we might be being robbed almost a milliliter of nutritious juice. We can't have this. Let's get on to trading standards. So, using a 5% level of significance and stating your hypotheses clearly, test whether or not there is evidence to uphold this complaint. So, are they skimming out some juice to save money, or are they not? So, first of all, we need to realise that a sample is being taken. So this here is for the entire population. So that's the distribution of juice amounts for all of these cartons. But now we're talking about a sample. So for the sample of 16, then what we're going to have here, this is going to be a different distribution. It's going to be the distribution of the sample mean, which again will be normally distributed with a mean again of 60, but now we divide this variance by the sample size. The sample size, as it says, is 16, so we're going to divide the variance by 16. And using a 5% of level of significance, what I'm going to suggest we do here is to just sketch out this normal curve. So do the bell curve like so. The mean here by H0 is going to be 60. I'm working back to front. It does say state hypothesis clearly. So H0, we always go innocent until proven guilty. So we assume H0 is that actually this company are telling the truth and that mu is 60. Whereas the suspicion is that actually they're putting less juice in these cartons. So it's a one-tailed test. We're looking at the lower end. The alternate hypothesis, which is a bit scary for this company, is that the mean is actually less than 60 mils. Now from this sample of 16, it's been found that the mean amount of juice per carton is 59.1. So 59.1 is down at this lower tail somewhere. So we need to find this proportion here, 59.1 or less. We find this proportion and then compare it to the 5% level of significance. So using this here, because this is a sample of 16, this is a distribution of x bar. So x bar is this distribution of, drawn out here, x bar normal, 60 with a variance of 3 squared over 16. So what is the chance of having this probability down here? So we need to work out the probability of x bar taking a value of 59.1 or lower. Last lesson we did continuity correction, right? So I'm just going to mention here, we don't need to do a continuity correction here because liquid is already a continuous variable. So don't be thinking we need continuity correction here because this here is already a continuous variable. So x bar, what's the chance of that being equal to or less than 59.1? This is where we have the luxury in 2022 or beyond if you're watching later of having decent calculators which can do the hard work for us. So what we can do here is go into the correct mode, which I'll show you now. So press menu, then 7, we're wanting normal CD. So we want 59.1 or less to be calculated. So put the lower bound as something approaching negative infinity, at least 5 standard deviations below the mean. I always go for the standard minus 999,999, or 6 nines for the upper bound, if we're looking at the higher tail. The standard deviation is going to be the square root of this variance. So it's the square root of 3 squared over 16, which you can see here is 0.75. I've messed that up, haven't I? Sorry, that was meant to be for the standard deviation here. Apologies. And the upper bound size 59.1. So just check I've not mispressed now. Lower bound good, upper bound 59.1 mil, standard deviation 0.75, and the population mean assumed to be the sample mean 2 is 60 millilitres. So press equals and equals again. Our probability is 0.1151. 0.1151. So this bit of a curve here is about 11% of the entire population, of the entire sample rather. Now, we wanted a 5% level of significance. 5% is less than this tail in green. 5% would only be about half of this tail in green. 5% point would be from this point here downwards. So 59.1 isn't in the critical region. Therefore, 59.1 is not statistically significant. Essentially, we just say here that this is greater than the significance level associated with that tail. That 5% level of significance is smaller than this observed probability. So therefore, we do not reject H0. We accept H0. In other words, not enough evidence to uphold this complaint. Not enough evidence to uphold complaint. Now, not in these examples, but in some examples and some exam papers, you might need to find a critical region or critical value for a hypothesis test for the mean of a normal distribution. You might have to standardize your test statistic into the standard normal distribution. And if you do have to do this, often you don't, but if you did, you do it in exactly the same way as before, which is subtracting the mean and then dividing through by the standard deviation. So, for the sample mean of a normally distributed random variable, where we have x bar, which is normally distributed with sample mean mu and sample variance sigma squared over n, then we can code this into the standard normal by taking the population, x bar, minusing mu, so minus off the mean, and then divide by the standard deviation, which is the square root of this. Square root of sigma squared is sigma, square root n, root n. So we take all values on the curve, subtract the mean, and divide through by the standard deviation, which is a square root of that. That will also be normally distributed as well. So sometimes you need to know how to do this, sometimes you can get around it by using the calculator instead. Typically, you need to code into the standard normal distribution if you don't know the population mean, you don't know the population variance or standard deviation, or you don't know any of those. If we do know those, typically we don't need to code unless a question makes it specific and says you have to, but that's very rare indeed. So coding test statistic in this way, it can be useful for finding critical values in critical regions, but like I've said, alternatively in some questions you might be able to find these directly by using your calculator. If you can use your calculator and avoid the coding, my suggestion would, to avoid doing that, let the calculator do as much of the work for you as possible. So a second worked example. We've got a machine now producing bolts of diameter d, where d is normally distributed with mean 0.580 and a standard deviation of 0.015. So right away we can just take this information and put it into the right wording. So d therefore is normal with a mean of 0.580. The standard deviation is 0.015. And that's for the entire population. That's for all of these diameters. It then says, though, the machine's serviced, and after the service, a random sample of 50 bolts from the next production run is taken to check if the mean diameter of the bolts has changed from 0.580. The distribution of the diameters of the bolts after the service is still normal, still has a standard deviation of 0.05. So this is the distribution of a population. We can now consider the distribution of the sample mean. So the sample mean, d bar, distribution of the values of the mean diameters from the sample, will be normally distributed. We've been told that the mean diameter, we assume it's the same as before, so we go for 0.580. We'd always assume that the sample mean is the same as the population mean. And here, the distribution of diameters of the bolts after the service, it's still normal, and the standard deviation hasn't changed. So this is standard deviation, so we square that, I should have done. And over here, because now it's a sample, we take the variance, 0.015 squared, and we divide through by the size of the sample. So here, in the sample, we're taking 50 volts, so we divide through by 50. So we need to find at the 1% level of significance the critical region for this test, stating the hypotheses clearly. So for A, H0 is either innocent until proven guilty, or no change, either or. So here we're going to go for there's no change. So we are going to go for assuming that the mean is unchanged. The mean would go for 0.580 still. The population mean 0.580. Whereas H1, we're just trying to test if the mean has changed. It doesn't say increased or decreased, just simply changed. So here, we'd test if mu is now simply not equal to 0.580. And again, what we can do here is we can sketch out this curve to get a better picture of what's going on. So again, we're going to assume it's 0.580. So this is 0.580, like I say. And I'm wanting here 0.5% in each tail. So I need to find this critical point here, which I'll call C1, and this critical point here, which we'll call C2, which is going to give us 0.5% of the curve. So as a decimal, this proportion of the curve needs to be 0.005, because that's what 0.5% is as a decimal. This here, as well by symmetry, needs to be 0.005. So we need to find these critical points C1 and C2. So we know the proportion of the curve we need. We know the area we're after is 0.005. We need to know the value that gives us that. Whereas normally you work out the value, and then from the value the calculator will tell you the area or proportion. So because this is the other way around, this is a question where we can use the inverse normal function. So I'll show you how to do this. So what we do here is we go menu 7, inverse normal. Now the area we need is 0.005. Sigma, the standard deviation, is the square root of this variance, so we do the square root of 0.015 squared divided by 50. Mu, the sample mean, we assume to be the same as population mean, which is 0.580. And we press equals, and we generate the required critical value, which is 0.575. Do the same for C2. C2, the higher end, this bit needs to be 0.005. That means all the stuff before it must be 0.995. So for the upper one, we can just change the area to 0.995. Mu and sigma are unchanged. We get here for that one 0.585 to 3 significant figures. And as you can see, there is a symmetry. That one's 0.005 away. That one, C2, is 0.005 away. And that's because the normal distribution is symmetrical. So therefore, the critical region is anything less than 0.575. So the critical region is where D bar is either less than 0.575 or where D bar in this higher tail is greater than 0.585. So I'll just add these critical values on just so you can see where they are. 585 here, 0.575 down at this end. For part B, it says comment on this observation in light of a critical region. So what was observed? What it says here, the mean diameter of a sample of 50 volts is calculated to be 0.587 centimeters. So think about where this would be on the curve. 0.580, 581, 582, 583, 584, 585, 586, 587 is somewhere here. In other words, it would clearly be in the critical region. So because 0.587 is in the critical region, we would reject H0. So this result is statistically significant. So one more example. This one's been taken from an exam and slightly adapted by myself. So we have a shopkeeper who knows from past records that 15% of customers buy an item from the display next to the till. After refurbishment of the shop, what he does is he takes a random sample of 30 customers and he then finds that only one customer has bought an item from this display till. So stating your hypothesis clearly and using 5% level of significance, test whether or not there has been a change in the proportion of customers buying an item from the display next to the till. So what I'm going to say here for A is let D be the distribution, not P, distribution of number of 30 customers buying an item from the display. Now in that case, either buy an item or they do not. So D is going to be a binomial distribution. There's going to be 30 customers. It says here there's 30 customers. And the proportion of customers that are believed to be buying from a display is 15%. So the proportion is 0.15. So therefore we're wanting the probability that D is less than or equal to 1, because only one customer's bought an item from that display till. So what's the probability that D would be 1 or less? So we just work out the probability it's 1 or less based on this binomial here. So what we're going to do, press menu 7, we're going to go down to binomial CD, go to variable, we work out a probability that only 1 out of 30 of these customers with a proportion buying an item of 0.15. What's that probability going to be? So we press in and see what probability we get. We get here 0.0480. 0.0480. So what we need to do as well, as I should have done at the beginning actually, is to state H0. So H0, we'd assume no change. We'd assume here that the proportion of customers buying an item is 0.15. For H1 though, what we're testing is if or not there's been a change. So H1 doesn't say which direction the change is in. We have to go the proportion is not 0.15. And so this is going to be a two-tailed test we're performing. And we've worked out the probability of 1 or less is 0.0480. If it's a two-tailed test and a 5% significance level, then this is 2.5% in each tail. So this value here, we compare it to 2.5%, and we can see that this is about 4.8%. So that's greater than the 2.5% in each tail. That's greater than 0.025. So for this one, we therefore realise that this statistic is not critical, because this is greater than the significance level in this tail. We therefore still accept H0. In other words, there's no change in the proportion of customers buying an item from that display. No change in proportion of customers buying an item from the display. So, for B here, it says during the refurbishment, a new sandwich display is installed. So a new sandwich display comes on board and maybe changes things. So before the refurbishment, 20% of customers bought sandwiches. The shopkeeper claims that the proportion of customers buying sandwiches now has increased. He selects a random sample of 120 customers and finds that 31 of them have bought sandwiches. So what we need to do here is use a suitable approximation and state the hypothesis clearly, test the shopkeeper's claim, use a 10% level of significance. Now, I've edited this question, okay? The only approximation to the binomial you need to know for the A level, unless you're doing further maths, is it would have to be the normal approximation. So suitable approximation, that's the normal approximation. It's the only one we can use. So we're told, essentially, if it's an approximation to a binomial, it's got to be the normal one. So first of all, we need to say what the original distribution would be. So there's 120 customers and they're buying sandwiches. So let's go for S. So S for sandwiches. So S would be actually binomially distributed because people either buy a sandwich or they don't. So 120 people by H0, the proportion buying a sandwich is 20%. So we put here 0.20. Now we approximate, so that's going to be approximately equal. So if S is binomial, I'm going to go one letter up. After S comes T. I can approximate this by T being normal. The mean is N times P, so 120 times 0.20 gives 24, and the standard deviation is 120 times 0.20 times 1 minus 0.20. So 120 times 0.20 times 0.80, because 0.80 is 1 minus 0.20. So that tells us that the variance, not standard deviation, the variance of the normal approximation is 19.2. So, next up, we're told at this point about the store, we need to then now test this shopkeeper's claim, don't we, using a 10% level of significance. So, this shopkeeper is claiming that the proportion of customers buying sandwiches has increased. So here for B, if I just make a bit more space for myself for B, we need the hypothesis. So H0, always go that there's no change. So for H0, we'd assume that the proportion is still 0.20. Whereas for H1, this manager seems pretty keen to show that this proportion's increased. So H0 is, we're going to see if it has increased the proportion of customers buying sandwiches to something more than 20% of them. At this point now, what we can do is think about this on the curve. So imagine this as the curve. This is the normal approximation. So let's call this T, normal, 24, 19.2. So the expected mean is 24, but actually 31 of them brought sandwiches. Now here, this is the distribution of number of customers. Okay, number of customers is discrete data. So we now need to go from a discrete measure, which is binomial, to the normal approximation, which is continuous. So we need continuity correction here. So we're wanting an approximation for working out the probability of having 31 or more customers buy sandwiches. So we want to work out the probability, an approximation at least, to a probability that 31 or more customers actually bought sandwiches. Well, that's approximately equal to T being at least 30.5. 31 needs to be 1 unit wide on a continuous distribution. So we assume 31 starts from 30.5 all the way up to 31.5. Because we're including 31, we start at the beginning of the unit, which is 31. So 1/2 of a unit less than 31 is 30.5. So using the normal approximation, we're trying to find this area here. So we're after the probability that the normal approximation takes on a value of 30.5 or greater. So at this point here, the calculator can actually pick up and do the hard work for us. So we're going to go Menu, Option 7, Normal CD. The lower bound is 30.5. The upper bound is as high as we dare go. The standard deviation is the square root of 19.2 for this one normally. However, that should give us a approximation. Yep, there we go. And next we do the mean. The mean for this one is 24. So press 24 for the mean, press equals, and then press equals again. And we then get a probability of 0.06898. So about 0.670, 90. Now importantly, this one here is going to be greater. This value here, sorry, is less than the critical value for the significance level. So if the significance level is 10%, this is actually less than 10%. So therefore, there is evidence here to reject H0. In other words, the shopkeeper may well be correct. Reject H0. Shopkeeper likely to be correct. By this test at least. Now for C, the store manager believes that the claim should not have been tested using a normal approximation. So 1 marker, I added this one in. Give a mathematical reason why the area manager may be correct actually in thinking that normal might be the best bet. Well, for this one here, we can say that this p-value here is 0.20. Think what it should be close to be modelled by a normal. It should be close to 0.50. So what we say here, oops, just move it out of the way. So the p-value, the proportion of customers who bought sandwiches via H0, it's not close to 0.5. So because it's not close to 0.5, 0.20 isn't really a good candidate for using the normal approximation. You still can use normal approximation, but it's not going to be a very good approximation at that. If p was about 0.45 or 0.48, fine. 0.20 though is a bit far out really. But because part B forces you to use an approximation, and the only one you can use for the binomial is the normal, then you had to use a normal approximation because the way the question was constructed. Now you need to try some of these on your own. So if you turn to page 58, exercise 3G, and try these question parts. So 1, ACE, 2, that should say ACE as well. Question 5, 6, 7 and 8, and let me know how you get on. So thank you very much for watching. Hope you've enjoyed it and found it a bit useful. Well, maybe not enjoyed it, but hope you have found it useful anyway. Take care, and I'll see you all soon. So from me, goodbye for now.